In this lesson, we will explore the concept of linear transformations and their applications. A linear transformation is a mapping between vector spaces that satisfies two properties. First, additivity. This means that the transformation of the sum of two vectors is equal to the sum of their individual transformations. Second, homogeneity. This means that scaling a vector before the transformation is the same as scaling the result of the transformation. Let us consider some examples of transformations. The first example is a scalar transformation, where t of x is defined as 2x. To test the linearity property, let us evaluate t of x plus y. T of x plus y equals 2 times x plus y, which expands to 2x plus 2y. This is equal to t of x plus t of y, demonstrating the property of additivity, as the transformation of the sum equals the sum of the individual transformations. Now, let us check the second property, homogeneity. T of Cx equals 2 times Cx, which is equal to C times 2x. This simplifies to C times T of x. Since both additivity and homogeneity are satisfied, this transformation is linear. On the other hand, consider a transformation, T of x defined as x squared. This function is not linear because T of x plus y equals x plus y squared, which expands to x squared plus 2xy plus y squared. This result is not equal to t of x plus t of y, which is simply x squared plus y squared. Since it fails to satisfy the additivity property, this transformation is not linear. Now, let us explore matrix transformations. Consider the transformation T of V defined as A times V, where A is a matrix with entries 2, 0, 0, and 3. To verify the additivity property, we calculate the transformation of the sum of two vectors and compare it with the sum of their individual transformations. Let U be a vector with entries U1 and U2, and V be a vector with entries V1 and V2. The transformation T of u plus v is given by A times u plus v. Substituting, this becomes a vector with entries 2 times u1 plus v1 and 3 times u2 plus v2. Expanding, this gives 2u1 plus 2v1 and 3u2 plus 3v2. Next, we compute T of u plus T of v. The transformation T of u is the vector with entries 2u1 and 3u2, and T of v is the vector with entries 2v1 and 3v2. Adding these two vectors yields the same result as T of u plus v, confirming the property of additivity. Now, let us check the homogeneity property. Consider a scaled vector c times v. The transformation T of cv given by A times cv. Substituting, this results in the vector with entries c times 2v1 and c times 3v2. Factoring out c, this simplifies to c times t of v, which confirms the homogeneity property. Since both additivity and homogeneity are satisfied, this matrix transformation is linear. This demonstrates how matrix transformation preserves the structure of vector spaces and fulfills the requirements of linearity. Scaling transformations adjust the size of a vector by stretching or compressing its components. For example, consider a scaling matrix in two dimensions, which multiplies the x and y components of a vector by different scaling factors. If we take a vector with entries 2 and 3 and apply a scaling matrix with the scaling factors 2 and 3 respectively, the result is a new vector with entries 4 and 9. This operation is linear because it satisfies both additivity and homogeneity. Now, let's look at rotation transformations. A rotation matrix rotates a vector counterclockwise by a specified angle. For example, rotating a vector with entries 1 and 0 by 90 degrees using the rotation matrix results in a new vector with entries 0 and 1. Like scaling, rotation is a linear transformation because it also satisfies additivity and homogeneity. These examples of scaling and rotation illustrate the powerful way matrices can transform vectors in a linear manner. Mastering these transformations is essential for understanding complex data manipulations in advanced fields like data science and artificial intelligence.